is Neha Rai. She is a research scholar at Department of Mathematics, IIT Roorkee. She will be talking about maximal density of integral set with missing difference. So Neha, you can
Thank you, sir.
start.
Thank you so much. And thank you very much for giving me this opportunity to present my work here. My title of the talk is Maximal Density of Integral Set with Missing Difference. This is joint work with my supervisor, Dr. R.K. Pandey. This is the outline of my presentation. This number theory problem started with the question asked by Moshkin, that he asked that suppose for a given set M of positive integers, how dense a set can sorry how dense can a set S of positive integers be if no two elements of S are allowed to differ by an element of M? What he mean to say that if suppose we have a given set of positive integers, say we have a subset of natural numbers, say 2, 3, 4. So we have to find the set in which the difference of any two element does not belong to this set M. Means the difference of any two element is either is not 2 or 3 or 4. So let us take example, let us take S as a set of multiple of 4. So difference of any two element is does not belong to the given set of 2, 3, 4. So we have this type of infinite set, say S1, S2, S3. So we have to find the density of each set and then take the maximal of all the density depending on S. So this is a very difficult task to find all the infinite set and find the density and then take maximal of the set. And this is just an example for a set 2, 3, 4. If we remove this set or if we replace this set by A, B, C, D, so we don't know about the set S, so we can't find the density for S. So this is a very difficult problem in number theory. T.S. Moshkin was an Israeli-American mathematician and best known for his work in linear programming. The range of his work includes beautiful and important contribution to theory of linear inequality and programming, approximation theory, connexity, combinatorics, algebraic geometry, and number theory, and so on. These are the very important definition to work on this problem, or we can say to understand this problem more clearly. So for the study, the structure of subset of positive integers, many types of density are defined. Among them, the most common density is known as asymptotic density or arithmetic density, or we can say natural density. So this is the definition of asymptotic density. So for any real number, say x, the upper density for a set S of non-negative integers is defined as the limit superior Sx upon x, where x tends to infinity. Here Sx is the number of element in S which is less than or equal to S. Similarly, we define the lower density of S as limit inferior Sx upon x. If the upper density is equal to lower density, then we say S has density denoted by delta S. This is some examples. If S is set of even number, then S has density 1 by 2. If S is set of multiple of 3, then S has density 1 by 3. And if S is set of arithmetic progression, then it has density 1 by A. This is very trivial examples of density. Here the maximal density is basically supremum of the density over S. Here supremum run over S, here S is an M set. And M set is defined as like this: for a set S of non-negative integers with the property that whenever AB belong to S, this implies that their difference does not belong to M. And M is a given set of non-negative integers. So S is called as an M set. So our whole work is on this M set. This problem become more interesting due to its connection to different area of research under different name. This is equivalent to the fractional coloring problem or distance graph. It was proved by Cheng and et al. That for any finite set M, the maximal density is reciprocal of fractional chromatic number of distance graph generated by this set M. It means that finding the fractional chromatic number of distance graph is the maximal, and the maximal density of M set are indeed the same problem. And here the fractional cutting of graph G is basically a mapping C which assigns each independent set I of a graph G a non-negative weight say Ci such that this sum is greater than or equal to 1 for each vertex. And the fractional chromatic number of distance graph is the fractional chromatic number of any graph is defined as the least total weight of fractional coloring of a graph G. Since we talk about the distance graph in my problem, so distance graph is basically a graph in which the set of vertex is set of all integers, and two vertex are joined by an edge, or we can say two vertex are adjacent whenever their difference belong to the set M. Beside the above coloring problem, this problem also contributes in long-standing conjecture known as lonely runner conjecture, which state that if n runner runs on a circular track of unit length at a common starting point, and each runner has distinct speed and they have constant distinct speed, then there is a time t at which a runner is said to be lonely if it is at least 1 upon n distance from our other runner, and this time exists for each runner. So each runner become lonely at a time t, and this conjecture has been proved for 6 or less than 6 runners and is still open for 7 or more runners. And these lemmas are very important lemma for to calculate the maximal density. We basically use these lemma to find the lower bound for mu m, and the other lemma is for maximum find upper bound for mu m. This lemma is given by Haralambis in 1977. He gave that for m is a set of positive integers and c and m be any positive integers, they are relatively prime to each other, then this value is equal to kappa m, and this kappa m provides the lower bound for this mu m, and this kappa m play an important role to finding the lonely runner conjecture, or to establish the lonely runner conjecture, and where this mod of xm denotes the absolute value of absolutely least remainder of x mod m. And this lemma 2 is the only results which provides the upper bound for mu m. This means for any real number alpha where alpha belongs to 0 to 1, and s be any m set, then this sx is less than s of k is less than or equal to k plus 1 times alpha, where s of k is number of element in s which is less than or equal to k, then mu m is less than or equal to this alpha. And this proposition, the next proposition is that when m1 and m2 are two sets, like the element of m2 is the multiple of some positive integers d, then their maximal density are equal. So in this in our result we take the GCD of the M set M is 1, and these are this is the remark given by Haralambis, and these three remarks are equivalent to each other, and this is actually equal to the value kappa m. So basically we use the third remark d3m to calculate the value of kappa m in our problem. So there are several attempts has been given. So in the past 6 decades or so, several attempts had been given to study mu m, but it has been founded exactly or estimated only in very few cases. So the very first result is given by Cantor and Jordan in 1973, that they found the formula for mu m when the cardinality of m is less than or equal to 2. Means when the cardinality of m is 1, then mu m is equal to kappa m, which is equal to half, and when m is 2 element with GCD of m is 1, then the mu m is equal to kappa m, which is equal to this value. And this is the in this case mu m is equal to kappa m, and this is basically a only general case in which problem is completely settled. And here we can see that the mu m is equal to kappa m for m has 1 element and m has 2 element. But this is another conjecture that the mu m is equal to kappa m in the case m is cardinality of m is 3 or 4 or 5. This is another conjecture. for mu and kappa m. So for cardinality of m greater than or equal to 3, the value of maximal density are known for several special case families of the set of m. In 1977, Haralambis determined the maximal density for the family, for this 3-element family 1xy, and gave the lower upper bound for the density, maximal density for the 4-element family 1 to xy. And for the very general set of 3-element, say xyz, Gupta gave a lower bound for mu m and proved that some specific cases these bound are exact value of mu m. In 2004, Liu and Zhu completely determined the value of maximal density for the families x, y, x plus y, and this a to a n times of family, cardinality of m is n. They also studied the family for this 4-element family x, y, y minus x, x plus y, and gave the lower bound for the maximal density mu m. Pandey and Tripathi also discussed the maximal density and kappa m for some special family of 3-element family, say AB and NA, NB, and AB n times A plus B. And Gupta and Tripathi determined the maximal density when element of M are in arithmetic progression. So also Pandey and Tripathi also investigate the maximal density and kappa m whenever M is either contains an arithmetic progression or contained in arithmetic progression. So this theorem is given by settled by Liu and Zhu in 2004. In this theorem, they discuss the family AB A plus B with condition that A is less than B and GCD of AB is 1. So the maximal density is equal to these value depending on B minus A is congruent to 0 mod 3, or B minus A is congruent to 1 mod 3 and 2 mod 3. Also they discuss the family, the 4-element family AB B minus A plus B. With in the theorem 1.2, they take A and B are of distinct parity, then the maximal density is 1 by 4. And in next theorem, next result, they take A and B both are odd, then the maximal density is greater than or equal to this quantity. So motivated by these theorem discussed by Liu and Zhu, we consider the 4-element family, say AB B minus A n times A plus B, and AB A plus B n times B minus A, which is generalization of theorem 1.2 and 1.3 and superset of theorem 1.1 respectively. Since we know that the maximal density of M is equal to maximal density of Km for any positive integers K, so it is sufficient to consider the case when GCD of M is 1. So this is our main result. In first we consider the family AB B minus A n times A plus B. So we divide the study according to the nature of A plus B is congruent to 0 mod 3, 1 mod 3 or 2 mod 3. In the very first theorem, we take the condition that A plus B is congruent to 0 mod 3 and n is greater than or equal to 1. We find the bound on kappa m. This kappa m is greater than or equal to these values. Depending on B is greater than 2A and B is less than 2A. Here M is, in the very first case, M is the sum of last two element, and in the second case, M is sum of first and last element. In the next result, we take the condition on A and B as A plus B is congruent to 1 mod 3 for the same set, and there is another condition on N. For N greater than or equal to this value, we find the lower bound for kappa M, and this also a lower bound for mu m. And in next, this is an observation that for any positive integer, say AB, with the condition that A plus B is 2 mod 3 and L be any non-negative integers, then these set partition the set of natural number except this element. So in next theorem, we take the same set AB B minus A n times A plus B, and we take the condition on A plus B is congruent to 2 mod 3. And we set M is equal to B plus n times A plus B. Then for n greater than or equal to this quantity, the kappa M is greater than or equal to these value depending on n belong to the n1L and n belong to the n2 n2 n3L. And this corollary gives the some equality of some exact value of mu m. In this case, when A plus B is congruent to 2 mod 3, then then for n belong to n2L, this mu m is equal to kappa m, which is equal to this value if B is greater than 2A, and this provides the bound on mu1 and kappa m when b is less than 2a. So this is the next family we consider. We take a plus b n times b minus a, and we divide the study according to the nature of b minus a is 0 mod 3, 1 mod 3, and 2 mod 3. So in the first theorem, we take b minus a is congruent to 0 mod 3, and we take GCD of ab is 1. So here we found for n greater than or equal to 1, we found kappa m is greater than this quantity. And in this observation, we see that for any positive integer ab, with condition that b minus a is congruent to 1 mod 3, where k is non-negative integers, then this n1 and n2 partition the set of integers, set of natural number, lifting this set. So in the next theorem, we take our second family, and we propose the condition on a and b like this: b minus a is congruent to 1 mod 3. Then for n greater than or equal to 2a plus b minus 1 by 3, this mu1 is equal to kappa m, which is equal to this quantity if n belong to n1k, where m is 2a plus b, and this and for n belong to n2, this value provides the lower bound for kappa m, and now this is also provides the lower bound for mu. And in this next result, we take the condition on b minus a is congruent to 2 mod 3, and we set m is the sum of second and last element. So here we found the kappa m is greater or equal to this quantity depending on n belong to p1k and n belong to p2k unit p3k, where p1, p2, p3 is given like this. This here p1, p2, p3 is also is a superset of the set of natural number, where a and b have set of a and b be any positive integers with condition that b minus a is congruent to 2 mod 3, and here k be any non-negative integer. So this corollary gives the exact value of mu1 in the case when b minus a is congruent to 2 mod 3, and when n belong to p2, then this mu1 is equal to kappa m, which is equal to this quantity. So we the various coloring parameters of the distance graph GZM. So we also find bounds on the, yes sir. We also find bounds on the fractional chromatic number of distance graph generated by these family. We discussed in the main results. Further, we determine the exact value of chromatic number of distance graph generated by these family. So in this next result, we find the chromatic number of distance graph generated by these two set, this set m and this set. So the chromatic number of distance graph is equal to 5 if n is equal to 1 and a is congruent to b is congruent to 1 mod 2 and 4 otherwise. We discussed many more results also in paper, but since due to time constraint, I'm just finished here. So these results have been published in Taiwanese Journal of Mathematics. If anyone interested can access from here. These are the references. Thank you.
Any questions? So Krishna Arjun, I have one question. So
what about the what m is bigger than doing it only for elements, right? Or 5 elements. What if it is not that case?
I can't hear you properly.
you just come.
No, I was just asking. You are considering the case where m contains 4 elements, right? Four elements, A, B, and n into A.
Yeah.
What if m contains more than 4 elements? It contains 5 elements.
This is I told you earlier that the problem is completely settled for the cardinality of m is less than 2, means m has 2 elements, but is still open for 3 or more element. So I'm working on 4 element and 5 element also, but this is open problem. You can also work on this. There is some result on 5 element, but not in general. Very specific cases.
Is there any other questions? Online participants, any questions? You can unmute and ask the questions.